Mechanics, we were talking about here, quantum mechanics. Mechanics is kind of a series of mathematical equations that relate together. They're all related. And in those equations, there are going to be variables, and we call those variables quantum numbers. Now we have N, L, and M. Those are the three that we're worried about. And what the idea is that each of those three together are going to define one orbital, one pattern for the electron, one electron cloud. And it's sort of like those three together will bring out the address of any one pair of electrons. So the first one here, we're seeing the principal quantum number, N, and that's going to be the shell, and we've already seen that before, and it's pretty simple. They're all integers, and they can go 1, 2, 3, 4, up to infinity, although we usually don't go higher than maybe 7 or so. So N can be 1, 2, and 3, and we've already seen that when we were doing things like, that the energy of any level N is a number negative 2.178 times 10 to the negative 18th joules divided by N squared. Okay, so that little n is in there, that quantum number. That's just one of the variables in the equation. Okay, the azimuthal quantum number, or also called the angular momentum quantum number, that is telling us about the subshells. Okay, for example, like an s orbital, a p orbital, or d orbital. And the rule for that one is that it can be anywhere from 0 to n minus 1. Going up by integers. So examples a little better. If n equals 1, then L could be 0 or anything up to n minus 1, which is 0, so L can only be 0. But if n equals 2, then L can be 0 or L could be 1. And then when n equals 3, L can be 0 or L can be 1 or L could be 2. And the idea about this is, the higher level you go, the more options you have for L. And that's what happens with the subshells. So on the n equals 1 level, all you get is S. And on the level 2, you get S orbitals and P orbitals. And level 3, you get S, P, and D orbitals, etc., etc. And those are related mathematically to the value of L. Now then, the last one here, this M sub L, that is the magnetic quantum number that is dependent on L. It goes anywhere from negative L to positive L, and we'll see that again on a better picture on another page. But the idea is, let's say when L equals 2, then M sub L could be negative 2, could be negative 1, 0, positive 1, positive 2. So there are 5 values for that. And that's going to relate to like this picture up here, where there are 5 d orbitals. And the reason there are 5 d orbitals is because there are 5 values for M sub L. So you can see on this one it says negative 2, negative 1, 0, 1, and 2. Those are the values of M sub L. So this will make more sense as we practice. So in the notes we are asking about what would these wave patterns for the electrons, what are they going to look like? And those wave patterns come from, a mathematical function called psi. And this little psi, this little guy up here, that symbol is psi, lowercase psi. So when n equals 1, then we said before, well, when n equals 1, L can be anywhere from 0 to n minus 1. That means L has to be 0. And if L is 0, M sub L can be anywhere from negative L to positive L, so that means that it has to be 0. So this first orbital that we're going to get to, this is going to be called the 1s orbital, which we learned about a long time ago. Now what happens on this function is if you say, okay, I want to know where the electron is, then what you get is a curve that looks something like this. Okay, this is the psi, and psi is the probability of, well, it's the probability function for an electron. And the horizontal here, this is the distance from the nucleus. But what we really do is we really use psi squared. Now in this case, psi squared is going to look pretty much exactly the same as the psi, because if you square these numbers that come down, it'll make a big difference when we get negative values, and we'll see that later. So the way we interpret this is we say, okay, close to the nucleus, there's a good chance of finding the electron. So if I was starting right here at the nucleus, I would say, okay, I can find the electron, find the electron, find the electron. And the farther we get from the electron, the less chance we're going to find this. So I'm drawing a lot of little dots representing the idea that if I were to try say where's the electron at any one moment, well, there has a good probability of finding it really close to the nucleus and less chance of finding it farther and farther and farther out. And this could go on, infinitely. But you can see that that's going to be not that practical for trying to use it. So what we really say is, let's draw a surface in which we would find that electron 90% of the time, and what we would get would be a sphere. So if I were to draw this and just, kind of, and this is our idea of an electron cloud, so a spherical electron cloud. So when we were saying that this is a 1s orbital, then we could say, well, that's a spherical orbital on the first level. Okay, 1s orbital. Now the second one, we're going to go back and say, okay, here's the 2, n equals 2. And when n equals 2, then L has two possibilities. L could be 0 or L could be 1. So we're going to see a couple examples here. So when n equals 2, there are possibilities as 0. And if L is 0, m sub L has to be 0. And what we're going to get our 2s orbital out of this. And what happens with this is our first function looks something, I'm going to change that. Our first function looks like this. And what happens when we plot psi, that's not a 4, that's a psi, then it comes down, it dips below the 0 mark like this. And we say that this is, in phase and out of phase. Okay, but that's not very useful for trying to draw our picture, so when we do psi squared, that's a little better. And what would happen if we squared all these values, then it would come down, hit 0, and then come back up again. So there's always a probability that's going to be a positive or 0 probability of finding the electron. Well, what happens here is close to the nucleus, and we have a really good chance of finding the electron, like we did before. But what also happens is at some distance from the nucleus, then we don't find the electron anymore. But we do find it again farther out from the nucleus. So we get a pattern that has two parts to it, and that little circular node, okay, circular, but actually this is three-dimensional, so it would actually be spherical, but there is a node, and I'll kind of draw it in here in black. That represents right there 0 chance of finding the electron. And if we go back and say, okay, well, what would this look like? It would be a sphere again, if we looked at it from a distance. It'd be spherical electron cloud. But inside, if you could see inside, there would be this node. But from the outside, it looks pretty much the same as a 1s. So this is our 2s orbital. So it's a higher energy, but it still looks spherical. Now, when we said we had the n equals 2, there were two possibilities for for L. So L could be 0 or it could be 1. So here, let's look at what happens when it's 1. When it's 1, okay, then we have three possibilities for our m sub L. It could be -1, it could be 0, it could be +1. So we have three of these. We're going to do our same thing. We're going to say, let's look at the psi, okay, versus the distance from the nucleus. And what happens this way, we get a graph that looks something like this. That's sort of like a little bell curve. And we say, well, as you go out from the nucleus, okay, this answer is psi squared, pretty much the same. What happens as you go out from the nucleus, let's say here's the nucleus right here, then we can find the electron over here, we can find the electron over here. We can go both directions. But what happens as we interpret this, there is actually a cosine squared term somewhere in this mathematical formula. And what that means is if I go off to the right, okay, which is, 0 radians, then I have, cosine squared is 1. And if I go off to the left, cosine of 180 degrees, that is -1, but if I square it, that's 1. But if I go at 90 degrees up here, then what happens is I'm going to say cosine of 90 degrees or of 270 degrees is 0. So if I go up or down, there is no chance of finding this electron. So what I end up with is a good chance of finding the electron out in this direction or in this region. to the left and the right, and it's kind of oriented along one axis. So if I were to draw this as a just kind of showing where the surface where you would find it, there would be a chance of finding it over here and a chance of finding it over here. Okay, so I would have two big regions over there with a nodal surface right down the middle, okay, right through the nucleus. Now, because of the fact that this is oriented along one axis, okay, we're going to call this over here the 2p, and we might call it in the x direction. Okay, so the 2px. Now, there would also be a similar one where there would be 2p in the y direction. So if I were to do the same thing, I could have one x, y, and z, and I might have one going up and one going down. And the rest of this would look exactly the same. This would be psi, this would be psi squared. Okay, and I can do the same thing, only this time I'd have a region up here and a region down here. And those would be the two portions of this. You know, and then in this case, my nodal plane, okay, would go along this axis. So other than that, it would be a very similar sort of a look. And then I can have a third one where I have it along the z-axis. So I can have a 2p in the x direction, a 2p in the y direction, and I can have a 2p in the z direction. And we'll see a picture of this in a moment. So coming back here, we're saying that when we get to n tells us which level we're talking about. Level 1, level 2, level 3, level 4. Okay, but L is pretty critical. L is which orbital we're talking about. So when L equals 0, okay, when L equals 0, then that's an s orbital. When L is 1, it's a p orbital. Okay, when L is 2, it's a d orbital. And when L is 3, we get an f orbital. So let's think about it for a second. Let's say we were on level 1. Well, level 1, n equals 1, then there's only one value for L, and that's 0. Okay, so on the first floor, you know, of our Opau hotel, we only have one type of room. We have the s orbital. But when you get to level 2, then L could be 0 or L could be 1. So on the second floor, we can have 2s and we can have 2p. So we would have both of these kind of orbitals on that n equals 2 level. On n equals 3, there'd be 3 possibilities. So we'd have all 3 of those, and 4 and 5 and 6. So if we look at these orbitals, then the type of orbital goes along with L. So this must be an L equals 0, and this would be an L equals 1, and an L equals 2, and L equals 3. And it actually keeps going. So there's an L equals 4, and those are G orbitals. And there's an L equals 5, those are H orbitals. So S, P, D, F, G, H, I, J. And here's our listing again. So back here we're talking again that for any level, you know, it can go 1, 2, 3, 4. And on that level we get various numbers of values for L. And it works out that on level 1 there is one type of orbital, because there's only one value of L. On level 2 there's 2 types. On level 3 there's 3 types. On level 4 there's 4 types. And then we said for the orbital, like we just showed a minute ago, that there were p orbitals. There were 3 different values, and you can see that one of these is oriented along the x-axis, okay, one along the y-axis, and one of those is along the z-axis. So this is the y-axis, the z-axis, the case up and down. And they would have different values for L, and you can see, it's kind of hard to see, but p negative 1, p 0, and p positive 1. Those are the 3 values, and they don't necessarily relate to x, y, and z because there's no set x, y, and z value on an atom. But there are 3 values and there are 3 directions. Okay, when we get to the D's, okay, then the similar idea. There are 5 m sub L's because it goes negative 2, negative 1, 0, 1, and 2. And there are 5 different orientations for that orbital. And the same thing when you get to F's, it goes anywhere from negative 3, negative 2, negative 1, 0, 1, 2, and 3. So there are 7 values for m sub L, and there are 7 orientations of the orbitals. So what we're asking now is, say, let's go back to this picture, and we've seen this before. This is our orbital diagram, and what this means is, you know, this is energy potential energy of our ideas. And as we're filling up electrons, we said we can put one into 1s and another into 1s, and then we can put them into 2s. And we've done this idea before. But what we're asking right now is, well, how do the variables go with this? And the variables are pretty easy. So, the n equals 1, and they're really obvious because here's n equals 1. So that's for this guy, this orbital down here, then the n value is 1. For both of these, n value is 2. Okay, for the n, when n is 3, it's all of these guys. Okay, when n equals 4, it's these ones. Okay, n equals 5, and we stop showing some of the other ones. But for each of these here, the value of n shows up as the front of that number. So if I say a 4d orbital, then I know that n equals 4. Pretty obvious. Okay, when n equals 4, there are different values for L. L can have values of 0, 1, 2, and 3. Okay, so there are 4 possibilities. And when L equals 0, then we are talking about the 4s orbital. When n equals 1, okay, then we are talking about the p orbitals. When n equals 2, then we're talking about the d orbitals. And not shown is the f orbitals. So when there's 3, then there are also some 4f orbitals higher up. So the value, when n equals 4, you do have possibilities for L. And because you have 4 possibilities, there are 4 different types of orbitals on level 4. So what we're asking is to go back now and look at these orbitals and say, okay, what are the quantum numbers that go with each of these orbitals? So we're going to try to draw those in. So when it's 1s, we know n equals 1. So I'm going to say n and L and m sub L. So 1s is L. Okay, 1s, the n equals 1. L, because it's an s orbital, that means this is 0. Okay, so this one is going to be 0, and this one's going to be 0. So that second, the one's going to be 0. And when L is 0, m sub L, okay, if L, I'll make a little chart. If L is 0, then m sub L has to be 0. When L is 1, m sub L can be -1, 0, or +1. When L is 2, m sub L can be -2, -1, 0, +1, or +2, etc. So for my first one here, this has to be 1, 0, 0. So the 3 quantum numbers that define a 1s orbital have to be 1, 0, and 0. For a 2s, it has to be 2, 0, and 0. Whenever I have s orbital, that third number has to be 0. Okay, so 4, 0, 0, 5, 0, 0. Let's go back to the 2p. Okay, for 2p, then the level 2, so n equals 2. And when n equals 2, L has a value of 0 or 1. But if it's a 2p, then we're talking L equals 1. Okay, and with 3p, L equals 1. And a 4p, L equals 1. And a 5p, L equals 1. And 6p, 7p, 8p, like that. Okay, then the last one's here. I have 3 possibilities, so when L equals 1, and m sub L can be -1, 0, and +1. So I'm going to put those 3 in here. And those are my quantum numbers for those 3 orbitals. And the same thing for my 3p. One of these is -1, one's 0, one's +1. For the 4p, one's -1, one's 0, one's +1. And for 5p, one is -1, and we have 0, and we have +1. Now again, there's no special correlation. It doesn't necessarily go -1, 0, and +1. There are just 3 values for m sub L, and there are 3 orbitals. When we get to the d's, okay, because it's a d orbital, then I know that L equals 2. Remember, for the s, p, d, and f, L equals 0, L equals 1, L equals 2, L equals 3. So d orbitals, L equals 2. So on all of these, I can put in a 2. So if I say 3d orbital, then I know the n is 3. And if I know that 4d orbital, I know that n equals 4. And because it's d, then I know that L equals 2. Now, I have values for the last ones, and it can be anywhere from -2, -1, 0, 1, and 2. -2, -1, 0, 1, and 2. And that's how I can assign 3 values to each one of these. So if a question came up, like on a test or quiz, and said, okay, here's a 3D orbital, give me the 3 quantum numbers that define that orbital. Well, if I say 3D, then I know that n has to be 3. There's no question about that. The fact that it's D, I know that L has to be 2. There's no question about that. But M sub L, I actually have 5 good answers. So there would be 5 possible answers for give the 3 quantum numbers of a 3D orbital. We could go the other way around. We could say, okay, I'm going to give you some more, but I'm going to say I have a 3, and I have a 2, and I have a 0. Okay, what orbital am I talking about? Well, we don't really need the last one. Okay, it's really a 3D orbital. We would just know that. And that's the idea of quantum numbers.